So I quickly recall, okay, I forgot to mention the references. One is by Eliashberg and Mishachev. This is called Introduction to H-Principle. And the second one is by Geiges. This is, I think, flexibility and H-Principle. This title may be incorrect. Okay. So I quickly recall the definitions. So an nth order partial differential relation, or simply a relation, is a subset R in the RJETS space. And if we are considering fiber bundles over M, then R would be RJET space of the sections. That was our notation. So basically, you think of local section, local map F from open X to N, and an R may be thought of is basically RJET of F at X is nothing but this tuple of information. So they take values in appropriate spaces. So that was a partial differential relation, and we defined two spaces. One we call the formal solutions of the relation. They are nothing but the sections of the jet bundle. So jet bundle means that you have a bundle structure over this, and this X projects down to this. This is the fiber. So this is the space of formal solutions, meaning that there will be sections whose images will go inside R. So sigma has its image inside R. And solution R is the space of maps from M to N such that it's so if you look at the RJET map that we defined, so this is the section space of the RJET bundle. So solution space is nothing but the inverse image of this gamma R. And H-principle means when we say that R is said to satisfy the H-principle, implies that the induced map at the pi 0 level, this is surjective. That means, okay, let's see, because this was injective, as we showed that your solution space is sitting inside the formal solution space. And if you have any point here, that means a formal solution, then you can connect it by a path to a solution. And R satisfies, these are the definitions, one parametric H-principle means that pi 0 JR is bijective. So what it means is that if you have, say, two things, sigma, okay, so let's draw another picture. This is your gamma R, and this is your solution R, you take two solutions F0 and F1. So they are jets, I mean this is JRF0 and JRF1. Suppose you can join them by going possibly outside your solution space. But then injectivity of pi0JR tells you that you can homotop this path inside the solution space. That means finally you can push it into this. So that means the bijectivity of pi0JR. Okay. So we define also the Gromov's theorem, which says if your base manifold is open, see all discussion can go through over the sections of some smooth fiber bundle as well. R is an open subset, and then R is deep invariant. Then R satisfies one parametric, actually it satisfies multiparametric H principle, but let's write this one parametric H principle. And then as an application, we saw the following, that suppose you have some open manifold and you consider the differential relation as follows, that one jet of, so this is our fibration. This is the fibration that I will be considering. The relation was one jets of local sections of this, that means one forms, such that d alpha x whole to the power n. So I am assuming that this is 2n dimensional, this is not equal to 0. So first of all, what it says is that this d alpha x is non-degenerate. This is just a form, this is a linear 2 form on Txm. So you can view this R as follows. We constructed the one jet space of this, and from there we had the exterior bundle, and you look at both are over M. We constructed this map. We said that this is a affine fibration. That means the fibers are affine spaces, so they are contractible. And what is this map also we defined? So x alpha I x del alpha I del xj, this whole thing goes over to del alpha I del xj at x minus del alpha j del xi at x. So this is an onto map, affine fibration. The relation here can be written as, so correspondingly inside this I can identify some set R naught. So what is R naught? R naught is basically all omega x which are non-degenerate. X is in M. So in each level you are just, over each fiber you are looking at only the non-degenerate forms and take their collection. So that would be non-degeneracy is an open condition. If you precompose with a pullback by a diffeomorphism, that remains non-degenerate. So R naught itself is a open and deep invariant. And if you look at delta inverse R, so this is delta inverse R naught. So that will also be open and deep invariant. So Gromov's theorem will apply, and it will say that given any section of this, given any section of R, we can homotop it to a alpha such that d alpha is symplectic. Alpha means basically J1 of alpha. So given any section of R, I can homotop it to something which is J1 alpha, and how is alpha? Alpha such that D alpha is symplectic. That means I can deform it to a genuine symplectic form. Okay. Now, I want to reformulate this result in a different way. First of all, I can, as you can see that from here you have this, okay. Because delta has this property, what I can say is this, that the section space of R and the section space of R naught have the same homotopy type. Because the fibers are contractible. So what happens, instead of writing that every section of R can be homotoped to this, I can rewrite it as follows. So every non-degenerate 2 form on M can be homotoped to an exact symplectic form in the space of non-degenerate forms. So instead of considering the equivalence, so here I will be having the space, okay, this is omega 1 m, and I consider D going into omega 2 m. Here I consider the non-degenerate 2 forms, and here I consider the exact, 1 forms such that D of alpha is exact. Now D, this exterior differentiation, will define actually a weak homotopy equivalence between these 2 spaces. So I don't need to really talk about the jets and others. I simply look at whether I have a non-degenerate 2 form on a space, and then I can say there is an exact symplectic form. The main point that is to be noted is that there was no differentiability condition on the right hand side. So you can use algebraic topological techniques to find whether such a thing exists or not. On the other hand, what does it say? It says that there is an exact symplectic form. Now suppose you have a manifold and H2, the second Theorem cohomology group, you just consider any representative of that. So suppose that alpha is some member of Theorem cohomology, then you can replace this by 1 forms alpha, so I think okay, something tau, okay. So 1 forms alpha such that also you take maybe omega naught such that omega naught plus D alpha is symplectic. So basically it says that you can also assign the cohomology class of the symplectic form that you get. Earlier it was the exact symplectic form, that means the 0 cohomology class. But it says that you can also prescribe any non-zero class as well, if there is any. Okay, so now this is all about the existence of, why I'm calling it existence, because I have reduced already the problem to the formal level. Okay, there is further thing that I want to mention is that, okay, there is the restatement again. So, okay, restatements. It says that the space of 1 forms, so, okay, the space of non-degenerate two forms on a manifold M has the same homotopy type as the space of almost complex structures. Okay. So what is an almost complex structure? We know that this is a bundle map such that if you compose J with J, then we get the identity. Now given any symplectic form, first of all, or for that matter, okay, suppose omega is a symplectic form. This argument will hold also for almost symplectic. That means, okay, these forms which are non-degenerate are referred as almost symplectic forms. Non-degeneracy condition is there, but this is a closed form is not there. So these are called also almost symplectic. It has a name. Okay. So if omega is a symplectic form, then there exists an almost complex structure J such that two conditions are satisfied. First one is omega u Ju is positive, and the second one, it says that omega is J invariant. So if you pull back omega by this automorphism J, then this is preserved. Okay. So these are the two properties. Now this existence can be done actually pointwise. The construction is this, you fix, so the construction is this, fix a Riemannian metric G on M, and then given this so G is symmetric, omega is antisymmetric, then we can define an A. So A is some bundle map such that this condition is satisfied because both omega and G are non-degenerate. Now you can show that, okay, you take this decomposition. From here, you can show that this would be positive definite, etc. And suppose I can write it as this, polar decomposition, and J has the desired property. So you can find this, all this discussion in book, this Magdav's book and other books as well. So this is the desired one. So whatever, you can fix some symplectic form or almost symplectic form, and then as you change your G, you get various structures which are almost complex structures. So there are many. So we have defined a map from the, say, almost symplectic, because this argument we have never used symplecticity actually, and from there almost complex. Okay, and this relation we say that omega and J are compatible. Okay, when J is related with omega by these two relations, we say that J is omega compatible. So starting from omega, this is a unique procedure which gives you this J. Let us call this P. Now, given this J, we want to show that these two spaces have the same homotopy type. So how to reverse this path? So now suppose start with J. So let J be an almost complex structure fix some G Riemannian metric, then define omega by this. So you can verify that omega and j, they are compatible, okay? So can verify that omega j is a compatible pair. Okay, so that means that this construction is a surjective construction. Now, we can also show that if you are given two members, so now suppose that your omega 0, omega 1 are such that these are compatible ones. Both omega 1 j are compatible. Okay. So I will want to show that you can join omega 0 and omega 1 by a path. Okay. So let us define okay. So now because these are compatible, I can define some Riemannian metric by this formula. This is the first property that we stated about the compatibility. So you define two Riemannian metrics. So G0, G1 are Riemannian metrics, and then you define this GT as the convex combination of them. So they are again, these are a family of Riemannian metrics. So what you can do, you can just write omega t by this formula. Omega t is, okay, so uv is gt juv. This basically reverses the role of omega and gt. You can prove because gt, this is a Riemannian metric, it will show that omega t will have the first property, and you can verify. So you can verify that omega t is compatible with j. Okay. So what does that mean? What we have verified is this, that we wanted to show that the space of non-degenerate two forms has the same homotopy type as the space of almost complex structures. What we have shown is basically that the pi 0 of almost symplectic and pi 0 of this bijection between these two almost complex. So at least in the pi 0 level, I have only said that D is a bijection between the connected components of these forms, that means the exact symplectic forms, and the connected components of non-degenerate two forms, that means the almost symplectic forms. Now we have shown that the almost symplectic form, pi 0 of the almost symplectic form is the same as the pi 0 of the almost complex structures. So the map that we defined in terms of D, we can go further. So, and we can claim that if we are symplectic forms to almost complex structures, so you have some alpha such that D alpha is symplectic. So that is how we do it. And corresponding to D alpha, we get a almost complex structure which is compatible with omega is equal to d alpha. Then this is at least at the pi 0 level, they are equivalent. So now you can see that if there is a manifold where you have found a almost complex structure, you know a priori, then that manifold will admit a symplectic form. It's the converse, provided your manifold is open. Now this result is surely not true for the closed manifold. You simply look at the S6, 6-dimensional sphere. It is known that this is an almost complex, it has an almost complex structure, but S6 does not admit any symplectic form. Because if it has to admit a symplectic form, then that must be an exact symplectic form, because what is the cohomology group? Second cohomology group is 0. So if it at all admits a symplectic form, it has to be exact. But then the manifold is compact without boundary. If you apply Stokes' theorem, that will lead to a contradiction, and so it cannot have. So the example is that it's a closed manifold. This is not true. If M is closed, then this result is no longer true. Look at M is equal to 6. This admits an almost complex structure, but does not have any exact symplectic form because of Stokes' theorem. Okay.
Lemma is true for
any pi I.
Any manifold, right?
Yeah, this is true for any manifold. Yeah.
And so to say that if the homotopy types are the same, so that
pi I you have to show. Actually, the fibers will be contractible.
Yeah, so but you have to show that it is a fiber.
Yes. And yeah, you can.
The fibers probably are contractible by this.
Fibers, yeah. If you assume this, actually you can show that. No.
Wouldn't it be like radially contractible or something? The fibers.
Fibers are
like omega 0 j and omega 1 j. Fix omega 0, then any other omega I.
Yes, that shows the fibers, yeah, contractible. But then other.
Be a vibration or something.
Yes, I can give you the reference. You can see. Basically, it is all about linear algebra at linear algebra level. You can see the book by. This is a very good, nice book. Again, I don't remember the. It's a very small book on symplectic. It's a very nice book. But it needs some construction. It's not very immediate. Okay. So far I haven't talked about the contact thing. So finally, let us write down what is the equivalent statement for the contact. What can you say when the manifold M is open and whether there exists a contact form or not? I mean by this is nowhere vanishing. Okay, so here is your differential part which is sitting. So I will state this as follows. So I introduce a definition. Of course, definition doesn't need open or anything. So a pair alpha is said to be an almost contact structure on M where alpha is a one form and is a two form, provided alpha wedge omega to the power n is non-vanishing. So it was alpha wedge d alpha to the power n non-vanishing means alpha is contact. So d alpha I am replacing by an arbitrary two form. So now there is no differentiability or anything here. So this can be viewed as a section of, so you can view this as a section of this bundle. You can view this as a section of this bundle. What the statement of the theorem, again it follows from Gromov's result on open manifolds. It follows that this the space of contact forms on M has the same weak homotopy type as the space of almost contact structures. Space of almost contact structures on M. So this will follow from Gromov's theorem by reformulation. Again, just like as we did in the case of symplectic, the J condition was reduced to almost symplectic condition. Here also the J condition of on alpha, which is contact, can be reduced to the condition that alpha omega, not the same alpha, some alpha omega being almost contact. Okay. So on open manifold, that as you can see, the problem can be reduced to the simply topological problem. So now if you have the solution at the topological level, that means if you do not have any topological obstruction, then you don't even have any differential obstruction as well. So H principle basically reduces a differential topological problem to an algebraic topological problem. Now, okay, so this is all about the examples. Now I'd like to outline the proof of Gromov's theorem as in a very concise way. No, lemma is there, that is known separately, and that doesn't require M to be open or closed. So together with Gromov's theorem, you can actually get that formulation. Because instead of saying something in terms of the J condition, it is always better if you can put it in the form of some differential structure or some. Okay. So, okay. So there are a lot of restrictions, as you can see. M is an open manifold, R is an open subset, R is deep invariant, and then certain things happens. We'll write just one step something which again you can write it as a theorem from which Gromov's theorem follows in just one step. So let's write it this way. So M is any manifold, and N is a submanifold of positive codimension. R satisfies, R is open and deep invariant. Then R satisfies H principle or one parametric H principle near N. So what do I mean by near N? So you have some manifold and your N is sitting as a positive codimensional submanifold. So it says that if you have a formal solution of the relation, then you would be able to get a solution which is defined on a neighborhood of this. It's not saying anything globally. You see that I have assumed M to be arbitrary. There is no extra assumption here. And from here, the Gromov theorem will follow by assuming M is open. We'll come to that. But let us understand this statement because it comes always in this kind of argument. Something is happening near M. That means around that N, there is a neighborhood on which certain property is getting satisfied. And that neighborhood might shrink in the process of argument. It is not any fixed neighborhood. So there will be several steps in the proof. In each step, we might have to adjust the tubular neighborhood of N on which that step will be valid. Okay? But finally, we will get some neighborhood of N on which we will get a solution of R. So basically this means that given any formal solution of R over open N, so I don't need the whole thing. I just need a formal solution which is defined over some neighborhood of N. I will always write open N. I don't specify the neighborhood. There exists a genuine solution F such that JRF is homotopic to sigma in R. That means the homotopy will consist of sections of R on open N. Again I am writing open N, but there is no reason to think that this open N is same as this open N. In the course of proof, you may have to shrink the neighborhood of N. But finally, you get some solution in the neighborhood of N. And then how to lift that solution to all of M if you know M to be open a priori. Okay? So these are the two things. So first let us assume this statement and deduce Gromov's theorem. This is simple. So proof of Gromov's theorem as a corollary. Okay, what we know about an open manifold. So M is an open manifold means that there exists a polyhedron, suppose this is N, there exists a polyhedron K of dimension strictly less than N, which is embedded inside M, and K is a deformation, you can also, okay, deformation retract of M. So what is an open manifold? It is either with boundary or it is non-compact. The most simple example you can see is that this is annulus. The whole thing, what is the K? You can take K to be something like this, and your whole manifold contracts onto this one-dimensional object. So basically, you have one free direction, means this dimension is one less than the dimension of the manifold here. That is will be becoming very useful in the course of the proof. So these things are open manifold. Closed manifold, if you know, see by Morse theory, if you have a closed manifold, then get a handle body decomposition, and you cannot miss the top dimensional handle, which is basically, so you cannot reduce the dimension by anything. So now, once you know this thing and you know this result, then what happens? You get, so there exists an isotopy delta t from M to M such that, okay. Now suppose you have, by this theorem, suppose you have got a solution on this. Let us call this U, this dotted neighborhood of N, let us call this U, and suppose you have got a solution over, okay, I have used N here, so suppose these are for some E over N for fibration. So you have a section of E only over U, not beyond that. See, E is a bundle over M, you have an N inside this, and I insert a open set here, and basically you have a section over this. Okay? So it says, this theorem says that you can get a section F which is defined on U. So I will get an isotopy delta T such that the final map, this is the identity map, and the final map will bring all of M inside this U. That is possible because you can deform everything onto K. So gradually you are deforming the space onto K. At certain point it must come within that neighborhood. Okay? This is pushing, just like that picture that we drew. If you push like this from here and from this side, at certain point you will be able to bring your manifold, I think I should use the within this small neighborhood. That is always possible. On which this neighborhood you have a solution. So if I precompose, because I have an action of the def on the space, and R is invariant, right? So what I will do, I will consider the two homotopies. Okay, let's write it down. First homotopy is delta okay, I missed one point. I have to write something here. So I want to prove Gromov's theorem. So we start with sigma, which is a section of R. And by this theorem, there exists an open neighborhood U of N with a homotopy sigma t such that sigma 1 is a genuine solution. That means it is the jet of the genuine solution. I don't distinguish between a genuine solution and a.
N here is the capital K, right? smooth version.
Yeah, so I haven't, yeah, exactly. Yeah. Actually, that is true for anything. I can replace n by some k. I have to do some more work only. So sigma 1, what is happening, the final map is pulling everything into this neighborhood. Okay? So delta 1 is mapping M, what should I say, inside this U, over which you have this homotopy. So what I do is this, delta 1 star sigma t, and I have another delta t star sigma 0. So there are two homotopies. Sigma 0 is sigma, okay? Sigma 0 is defined as a section all over M, so I can pull it back by delta t. See, I have the diff action. I'm not mentioning what is the action, that's all. So I have a diff action which keeps R invariant. So if sigma 0 is a section, then if I pull it back by act a diffeotopy on this, that will also be a section of R. Similarly here, sigma t is a section of R and I am pulling it by delta 1, so these are also sections of R. But what about the final one, sigma 1? Sigma 1 is of the form JR of F. So if you pull it back by delta 1, so what will happen, delta 1 star sigma 1, this will be JR F composed delta 1. I am becoming a little bit simplistic here, but there may be some complicated actions as well. Okay? So you have something which is JRF, and if you act by this, this is JRF composed delta 1. Because, so this is again a solution. Why? Because F was a solution on U, and then you are pulling it back by delta 1. The relation is invariant under the diff action. That means if you have a solution and you pull it back by diffeomorphism, it still remains a solution. So the final map here is a solution. Okay? And all these homotopies, okay. So each of these maps are sections of R since the relation is diff invariant. Already sigma t was sections of R, so if you pull it back by some diff action, that will also be section of R. And since the final map, and note that delta 1 star sigma 1 is coming from a genuine solution, because sigma 1 was a genuine solution on U, and you are pulling it back by delta 1. What is delta 1 doing? Delta 1 pushing everything into U, and here you have your sigma 1. So this is defined on all of this. So if you concatenate these two homotopies, this is a homotopy, this is a homotopy. Start from t is equal to 0, this is delta 0 star sigma 0, that means it is sigma 0, and what it ends with, that is delta 1 star sigma 1, which is coming from a genuine solution. So you have combined you have connected this sigma 0 with this, which is basically coming from a genuine solution. So this proves the H principle globally. See, at the intermediate stage, this sigma 1 was not defined on all of M. It was defined only on this part. Then you had to lift it to the whole of the manifold by using the diffeotopy that shrinks whole manifold inside that small neighborhood. This is the trick here. And this trick cannot be done if you do not have this extra free dimension. Okay. So that is the deduction of Gromov's theorem from this. Okay. what about the proof of this? I will very briefly discuss these things, main steps. But before that, so you have seen why I require M to be open. You have also seen one importance of diff invariance, but there are more importance of diff invariance that will come. Okay. So I prove this, okay? So this theorem. But before that, let me observe two things. Why I require R to be open? What are the consequences of that? So if R is open, there are two consequences. Suppose something, you have a local solution of, open X to E. E is the bundle, fibration. So this is, suppose this is a section of your bundle, and what you know is that this belongs to R. That means at one point it is belonging to R. Okay? This is a local section, at one point its jet is going inside R. But R is open. What does it say? It says that, see, all throughout I am assuming these are smooth. So this in particular, this is continuous. So this implies there exists an open neighborhood U of X such that JRFY belongs to R for all Y in U. This is by continuity argument. That means what? See, F was just a representative of the jet. So that, if I choose some representative, see, I could have chosen another representative. The maps will be different. At one point they may be same, but whatever representative I choose, this says that F restricted to this Y, or maybe I have to shrink the neighborhood again, because F may not be. So F restricted to Y is a solution. Solution of R over this small set U. So it just says if your function, I will call this an infinitesimal solution. That means it is satisfying the relation only at a point. I will call F an infinitesimal solution of R. That means F itself is actually a local solution. This is the major thing. So every infinitesimal solution is a local solution. So this is the first property that I will use. So if I had asked for a local solution of R, and I have a section which at one point is in R, that is automatically done. And now you see, suppose your manifold is just a disk. It is also done, right? The proof is done. It may be compact or open, whichever. By the earlier argument, because you have something, JRFX, at one point it is in R. So on some small neighborhood, it goes inside R. But then you can shrink the whole of the disk into the smaller disk by radial contraction. And then use the contraction maps to lift the solution on the small neighborhood to the bigger ball. This is the idea. So locally, if it is solved, then the problem is solved basically on all contractible species. So this is one property, that every infinitesimal solution is a local solution. The second property is more involved a little bit. Okay, let's consider two subsets, okay, A and B. So this is a topological pair, B is a subset of A and assume that both are compact, B and A are compact. So I consider the solutions of R over B and I restrict them solutions of R over, sorry, this is the bigger one, so A over B. And suppose I have a homotopy lifting problem. Suppose I have a homotopy lifting problem. That means I have a homotopy where each map is defined and it is a solution of R in a neighborhood of B. And initial map can be lifted to a solution of R on a bigger neighborhood. Okay? So you have this A and you have B like cylinders. So Ft are defined on some disk and F0 is defined something on a bigger thing. So fibration means this problem has a lift. So what I demand is that if your relation is open, so the initial map has a lift inside R and use the fact that R is an open set, then what you get, you can lift this map on some small interval you cannot lift the whole map, whole homotopy. Solution of R over A. So your manifold is M. You are getting a solution only on some small part. No, P is some polyhedron. Okay, you can ignore, let us ignore for this, just a compact space, some compact space. So this is required to state the homotopy lifting property. So what I need, what I can say, conclude that if we have a homotopy of maps which are defined on a neighborhood of B, where the initial map is actually extendable to a solution in a neighborhood of A, then you can get a lift F tilde not on the whole of this, but on some smaller 0 epsilon interval, such that each F tilde t will be an extension of the solution here. And this is again a similar argument. This is why I have chosen AB to be compact. So you have something defined on this which is going into, whose JR is going inside R. If you take any extension of this problem, that has to, for some small neighborhood of this cylindrical space, will go inside R, because R is open. You have a map, some compact set is going inside R, you consider any extension, whether that goes inside the solution space or not, I do not know, but because it goes inside the solution space on this compact set, it has to go there on a neighborhood of this. So there, by using that, you can get actually an epsilon. I'm not going into that detail, but basically this is the thing that you need, okay? Because of openness, you can lift a smaller thing. So this is, in Gromov's language, this is called microfibration. Usually I would say that this is a fibration if I have the whole lift. This is called the microfibration, means you have a small lift. And that plays a very important role in the proof. I will not go into the details, but I will just mention where you use this fact. So these are the two consequences of open manifolds, open relations. Now comes the most crucial part. So I will give a proof in a very, very restrictive situation, but that way we do not lose much of the proof. Here you see n has a positive codimension. So I assume that my manifold is simply some R2, and n is an interval, because let us consider interval. Why? I will tell you. Because given any manifold, you can get a triangulation of the manifold where each of this is some simplex, and what you do, you define the solution skeleton wise. First you define on the neighborhood of the 0 skeletons, then you define a solution in the neighborhood of the 1 skeleton, and go on like this. So what I will do, in a very restricted case, this is just a one small part. See, you will have a triangle in the 2 case, suppose. You already know that this first property of R enables you to get local solutions here, right? But then you want a solution on the neighborhood of this. But when you do that, you must have at least on some smaller neighborhood, the solution should remain the same. So you need some kind of an extension of the solution. So already you have solution, suppose, on this thing. So in the second level, what you will need, you will extend this possibly on some smaller neighborhood of this. So this is what I will explain. First part of the property of R ensures that at the 2 vertices you already have some local solutions. How I extend that solution on a neighborhood of the 1 simplex, that I will explain. Okay. So you have this picture 0, 1 by, let us call this property A, and let us call this property B. By A, we have solution on open neighborhood of 0 and on open neighborhood of 1. Okay? But then I want to extend this. Okay? Okay. Let us, for the time being, let us ignore the extension problem. Just suppose I want to define a solution in the neighborhood of this. How can we do that? Okay. So first let me write it down. So sigma, this is the initial map that I started with. This was a section of R. Okay? My aim is, of course, R2. Now I pick up, let's change the notation a little bit, capital A. So for each x in A, so sigma naught x belongs to R. Sigma naught is a continuous map. Now I want to choose a appropriate representative of sigma naught, and that should be chosen continuously. So what is the procedure? I take we choose, already see, already I have assumed that my manifold is R2. I can reduce. This is a very usual technique on manifolds. Because you know that manifold is triangulable, you divide it into small simplexes and argue that your bundle E that you was considering is locally trivial, means it's trivial over U, and transform the problem of sections to problem of maps. Okay. Anyway, so suppose this X, okay, this is R2, recall, and A is simply 0, 1. So what I know, how to choose sigma naught X? Because sigma naught X is nothing but, what do you need? This is X, some representative if you could choose, fx, this is del f, del xi, x, so del r something. So this is the jet, right? But this f, there may be many choices of f, for which this data would be the same. How do you choose an f? you know this value, just take the Taylor's polynomial corresponding to this. These are the coefficients of the Taylor polynomial. So now you know that sigma naught is a continuous section. For each x, you are choosing your representative in a unique manner, right? Because now everything is happening in Rn, particularly R2. So, sigma naught x, okay, given sigma naught x, choose Taylor's polynomial of representing sigma naught x. Just like if you have a linear map, you can define the first order linear map, okay? If I have to do whatever I do, I have to do it continuously. So I must have a unique way to define the primitive. This I will be calling the Taylor's polynomial, I will be calling primitive. Let us denote this by px. So the polynomial I am choosing in terms of x. So what is the property? Again, if you look at the JR of this polynomial and takes its value at x, this is same as sigma naught x. This is the infinitesimal information. Out of that I am considering a unique representative. And I have to choose that continuously, so this is the method I use. Okay. But now, so what I have, so on each point, around each point, I have a neighborhood. Okay. So further, I know that this belongs to R. So around X, there exists a delta neighborhood, say B delta X, on which this polynomial Px is a solution of R. Because it is a solution of R at one point, this Px must be a solution of R on a neighborhood. Yeah? Because of the openness of R. So I have on, this is my B delta. So B delta 0 and this is say B delta X. So on each of this I have got a local solution, but of course they don't match on the overlap. So the main problem is how to interpolate between these local maps and get something global on the neighborhood of a 0-1 interval. Okay. So this is the thing. I start from sigma naught x, which is in R, take the Taylor's polynomial representative Px, because it's x, j at x belongs to R, Px must be a local solution of R, and that is on some delta neighborhood. So what I claim is that you can choose this delta, positive number delta, uniformly for every point x. I'm not going to prove all these things. So that is the main thing. So every step you will see there is a uniform choice of such positive numbers. So there exists a uniform delta which works for all x in A. Okay? Yeah, compactness and openness. These are the basically topological things we will use. Nothing beyond that. All topological argument. We haven't patched.
That's the main thing.
Yeah, that will come to. So what I have said that I have a uniform delta which works for every point x, and on B delta x I have a local solution. That's
no, my intuition is the exact opposite. Patching is easy, and uniform delta is the hard to patch.
Uniform delta is just a set topological argument.
Uniform delta does not involve estimates on air.
Estimates on?
Reminder estimates on air?
No, nothing. It's purely topological. Like a Lebesgue number argument possibly. Okay. Or some variants of that.
Using in this compact, but there
compactness. 0-1 is. Yeah, but as I said, I have first of all started with some triangulation of this. I will do it locally. I will get a solution in a neighborhood of a simplex. And then, as I said, when I want to get a solution in a neighboring simplex, I have to respect this part. Not fully, but even partially will do. So I am not right now considering the extension part. I am just saying I will construct a solution on the neighborhood of this. Whether I can keep these ends fixed, that would be the secondary thing. Okay. So now how to patch these things? This is where the second microfibration property will come into play. Okay. So I will draw everything in squares. That is easier. Okay. So suppose this is a point X, and suppose you have got a solution. This is Px. You have got a local solution on this. Now, if y is close to x, then what happens? Then right? So I have a delta neighborhood about y. So let us call this B delta, sorry, this is B delta x, this neighborhood, and this one is B delta y. What I mean to say is the following: both Px and Py, they are defined on a neighborhood of x. They are close enough. Their domains are because I have chosen delta. So both Px and Py are defined on a neighborhood of this. So let us fix something. I take a very small neighborhood. Okay. And if I take it suitably, I know that Px and Py are also very close. Right? Because the way we have chosen the representative continuously, x and Py will be sufficiently close on this neighborhood if xy are sufficiently close. So if y is close to x, Px, Py are both, and not only that, we can ensure that Px, Py are epsilon close, means arbitrary close, I mean. Further, these arguments will tell you that if you choose y sufficiently close to x, then you can homotop Px and Py on a neighborhood of x. Okay, argue this way. Px value is going to some neighborhood, choose that contractible, and then choose y so sufficiently small, sufficiently close to x, so that this Py also maps a smaller neighborhood of x inside that contractible neighborhood. So you can contract, homotop. So on this set, okay, let us look at this. I have a homotopy. So we have a homotopy. So we will have a homotopy here. Okay. So the lower map is your Px and the higher map is Py. You can deform one to another, but you need a patching, right? Because on this set you have one solution, on this set you have another solution. If you look at the graphs, for example, one graph might look like this and the other graph will look like this at various levels. this I am considering the graph of Px, and suppose this is the graph of Py. They will be at different level. I have to get an interpolation between them. And this is an x here, this is an x here. So on this neighborhood, I have a homotopy between these two things. Okay. Now I look at this white square, and there you have a small pair, and I take a neighborhood along the, say, boundary. So I define a homotopy here. So you have a homotopy here. So this would be, okay, my capital will be at the picture, sorry, capital B would be this square together with this ring. Okay, and let's define it in a different, A I have already used, so let me do something C. C is the basically B delta x. That means this whole of the square. And this is the union. Okay? I have a homotopy on this between Px and Py. Here I have Px. Just one map, and I take the constant homotopy there. Okay? So I take a constant homotopy here on this region, and suppose I call this a H, I put H here. And at time t is equal to 0, I already have this Px. So Px is defined on the whole big square, B delta. So this can be related to a covering homotopy problem. So you have certain compact set here. Again, this is a compact set. This is the map Px, and you have a homotopy between homotopy of Px on this region. This is union this. How it is defined here? This is the homotopy H, and this is the constant homotopy. So I extend this. Of course, I cannot, because of this microfibration property, I cannot extend the whole thing, but what I get, let me write it down. So there exists a further delta 1 such that if your okay. I can partition the whole thing like this. So this is, say, k delta, and this is k plus 1 delta, and so on. So this would be my x, point x. What it says, if y and x are sufficiently close, y and x are, say, delta 1 close, then we have a solution to this covering homotopy property. Okay? I'm not going into the details. Okay? So you have the homotopy here between Px and Py. You have a constant homotopy here. and the Px is defined actually all of this. This data can be lifted, this homotopy can be lifted to all of this, okay, provided your x and y are sufficiently close. Okay? So that closeness delta 1 will come from this microfibration property where I explained something epsilon from there. Okay. So now how to patch these things. So let me draw a bigger picture. Of course, because R is open. R is open means you have the microfibration property, and that will leads to the lift of such a data.
Microfibration property and solution for R.
Okay, you can call it all those things. Solutions are embedded inside R. Actually, I do not need R. I need the solution space. Solution space, okay. Solution space of R is contained in the gamma R, right? So when I am considering the lifting, of course, I am always in space of solutions of R. So you have a function whose jet is inside R. So I just consider the jet map.
What I am trying to say is that for R, the microfibration property is clear.
That is really clear, huh?
But for sol R, it's not so clear because when you lift it, it may not be in sol R restricted to A anymore. It will be in gamma of R restricted to A.
No, it will be. I'll start from a something which is already a solution. It's the same argument will give. Which is giving you the microfibration property for R. Actually at the level of R, you don't just, you have the fibration property, you don't even have to come down to the level of microfibration. If you are considering R, section space of R over B and then restrict to over A, that restriction map is a fibration. Okay. Here, because of the openness of the property, I can explain it afterwards. It's not so difficult. Okay. So, this is suppose my K delta, which will be my X, and you have a something big here. Okay. On a small neighborhood, you have a homotopy, right? So let us denote this homotopy by, so it is a homotopy between Px and some Py. Y is sufficiently close. So I will take X to be some K delta and this to be K plus 1 delta. Let's, or maybe delta by 2, whatever, I don't know. So here, suppose this is my homotopy, HT. Okay. What I will do, so suppose this is delta 1, sorry. This would be, let me write, okay. This side. Okay, let me use some other chalks. On this side, let us put the map H1, whereas on this side, I put the map Py. Py is, y is 2k plus 1 delta, okay? So I put the map Py here and I put H1 here. What is H1? H1 is a homotopy between Px and Py, but only on some neighborhood of X, small, okay, some open X, some very small neighborhood of X. Okay, let's write it X, it's confusing. So this is X, okay? So right hand side of this, I put Py, left hand side, I put H1. What I know, H1 and Py agree on this small thing, but not outside that. because I have got a homotopy HT connecting Px and Py. So the final map H1 is Py, but only on a small neighborhood. So this small neighborhood I am showing like this. So I have to ignore this part basically. Here there is no match. So I remove this thing. So here this portion H1 and Py perfectly match because Py and H1 are same on this small neighborhood. So I put, so on the right hand side I Py, on the left hand side I put H1. So if I ignore this part, let's delete. So this is I cut out. This is the part I cut out from this. So now your space is not just square, but these portions have been deleted. So there is a match in the neighborhood because on this region H1 coincides with Py. Now I had Px somewhere, right? Px somewhere. So in between I take, so why I'll describe. So in between this is H1 and I will take, okay. So I take out again this part and I put here my Px. Let us see. So I have deleted from the square these slits and also deleted this part. I have put Px on the left hand side, I have put H1 here, I have put Py here. Let me see whether all these data match or not. They all match. Why? Because it has to match here, right? This has to cross over this. This is a continuity of the domain. This you have removed, so there is no problem of matching between Px and H1. But here, when you are putting, say, Px here and H1 here, then you have to see whether they match here. But look at the homotopy. How did I define the homotopy? The homotopy was throughout constant on this ring. So Px and H1 are same here on this. So there is no problem here. Here also Px is equal to H1. Now look at this part only. So here you have put Px, here you have put H1, here you have put Py, and all this data nicely match with each other. So the result again says that if xy are, say, at most sigma delta 1 distance apart, you can do this, you can get this picture for every such point, such pair of points. So all these piecewise data will nicely fit together. Okay? Here I am working with x and y. Now I will replace everything with x is equal to some k delta 1, y is equal to k plus 1 delta 1, and from here I will pick up some point in between because I have to patch these two together. So I will need some 5 more minutes maybe to finish it off. It's just, so what I have got, you have some, this was your A, yes, this was your A, and you have got a solution on this picture. Let's see. So there will be a picture like this. So these are removed. So I strike it out means these portions are removed. So you get we get a solution on the above domain. Let us close it by something. So suppose on this domain above, okay, but not on the whole. There are many points you have to delete. I cannot extract a neighborhood of this A from there, because at this point my solutions are not defined. So how to get rid of this? What we do now again we use this deep invariance property. So the picture is such that your A is I, and this direction is simply I cross some j, some interval. I choose some deformation. So this is an A, right? This is my interval A. I will deform it to something this. I can do it. You can use partition some bump functions such that the graph will look like this. So suppose there is a delta t, again, okay, I'll use some other notation, phi t, such that phi 0 is identity and phi 1 takes this A, which is my I, onto this picture. So I have a solution on a neighborhood of phi 1 I, because my solution is on the complement of this slits, and this phi 1 I is sitting inside the complement of the slit. So there I have a solution. So again what I do, I simply pull it back by phi t to bring it back on a neighborhood of this. What I did in the case of going from a small neighborhood to the bigger neighborhood. Exactly the same thing. Again my relation is diff invariant, so solution, when I pull it back by a diffeotopy, it will give me a solution now in a neighborhood of this. So if I have a homotopy between my initial sigma 0 with a solution, then that homotopy can be lifted back to a homotopy on this neighborhood. And that is what I required. Okay, maybe it's a bit complicated, but the higher dimensional things are not very far from this argument.
For triangle manifold, but generally open manifolds, three manifolds, they are not triangle.
You can get a triangulation, right?
Non-compact means you are open, so they are not compact. So you can't take non-compact.
I'm not, first of all, okay. You can always get a, this K which I chose, that was compact. Keta. That I used somewhere. K is a compact polyhedron.
So in that case, the A should be a compact manifold.
No. See, otherwise you don't get this free direction. Where do you get this free direction? A is compact, right? This was interval A was compact, but the neighborhood is not compact.
No, I'm talking A whose neighborhood you are taking. A
I think we can write down the argument for non-compact as well. But to prove this theorem, I do not need that. I just need to get a core compact on which this will be.
Actually, Gromov-Witten you are taking a polygon.
That's the same thing, yeah.
That polygon is a compact thing.
Yeah, polyhedron, yeah.